Hi students, in this video we're going to explain about complex numbers. If you remember in other classes when we try to solve the square root of a negative number, like for example, see a square root of negative 25, we said not a real number, right? So we wasn't able to solve, you know, this square root of negative 25 because it wasn't a real number. But if we use what is called the imaginary unit I, where this imaginary unit I is equal to the square root of negative 1, we're going to be able to solve, that issue that we had with the square root of negative numbers, right? So all is about to introduce what we call the imaginary unit I. So using this imaginary unit I, if I have to find the square root of negative 25, I'm going to say that this is the square root of negative 1 times 25, right? Okay, because negative 25 will be exactly the same that multiply negative 1 times positive 25. Using the using the product property of radicals, we're going to split this into radical expression. So square root of negative 1 times square root of 25. We know that this square root of negative 1 is I. So I'm going to have here I square root of 25. The square root of 25 is 5. So I'm going to have in this case just 5i. So 5i is the value, that you obtain, the result that you obtain when you find the square root of negative 25. Of course, 5i is not in the real number set. It's not an element of the set of real numbers, right? So once we know this imaginary unit I, we are ready to introduce what a complex number is. And a complex number in a standard form is a number a plus bi, where a is the real part and b is the imaginary part. And b is the imaginary part. So this is the standard form of a complex number. A plus bi is a number, that contains a real part and also contains an imaginary part. Now, when we are working with complex numbers, we're going to be able to do exactly the same operations that we do with real numbers, right? So the first I want to explain is how we add, the addition of complex numbers. So suppose we have the numbers 7 minus 3i plus negative 2 plus 5i, and I have to add these numbers. In the books, they will give you kind of formulas, let me say formulas, to perform this addition of complex numbers and the subtraction of complex numbers. But to me, it's really confusing, So I just explain this in a different way. I say, okay, I have the addition of these two complex numbers. 7 minus 3i is a complex number, and negative 2 plus 5i is another complex number. I have both numbers in parentheses, just like to establish the limits of each number. So the first I'm going to do is to eliminate the parentheses, so I'm going to drop the parentheses. using exactly the same rules that I use when I'm adding polynomials. So there is some visible positive sign here. So if I remove this parentheses, I will keep all the signs inside. So we say 7 minus 3i. I have another positive sign here. So when I drop the parentheses in this second complex number, as this sign here is positive, I will keep the signs inside. So I'm going to say minus 2 plus 5i. And once I have my numbers in this form, I will combine real part with real part and imaginary part with imaginary part. So 7 is real part, negative 2 is real part. And in this case, negative 3i is imaginary part and 5i is imaginary part. So in addition and subtraction, you combine real with real, imaginary with imaginary. So real with real, 7 minus 2 is 5. Imaginary with imaginary, negative 3i plus 5i, that would be just 2i. So what I got? 5 plus 2i. So when I am adding, the complex number 7 minus 3i plus negative 2 plus 5i, my solution is 5 plus 2i. It's super, super easy. Let us see how we subtract complex numbers. So let us think in the following example. So let us say we have this example over here that is 11 plus 14i minus negative 3 plus 2i, right? So in this case, I have my two complex numbers and I have a subtraction. I'm going to do exactly the same. I'm going to eliminate the parentheses. If I look at the front of these complex numbers, I don't see any sign, so it should be here a positive sign. So dropping the parentheses here, I will keep the same signs that I have inside. So I will say here 11 plus 14i. Just my first number just stay like that. And then I have this negative sign over here that is going to reverse the signs inside of the second parentheses. If I remove the parentheses, I'm going to say positive 3. And this positive turns into negative, so minus 2i. Okay, I had to reverse the signs inside because I had this negative sign. It's like you multiply negative 1 times negative 3 will be positive 3. Negative 1 here times positive 2i will be negative 2i. Now I will combine again exactly as I did in the other case. Real part with real part. And imaginary part with imaginary part. Right? So when you do that, you get 11 plus 3, what is 14? And 14i minus 2i, that is 12i. So in this case, my answer is 14 plus 12i. So I already did addition and the subtraction of the complex numbers. Let us then now analyze, the multiplication of complex numbers. So how do you multiply complex numbers? Let us see that. So to multiply complex numbers, or I'm going to start just explaining when we multiply a real number times a complex number, the imaginary part of a complex number times a complex number, and two complex numbers. So multiply complex numbers. And in the first example, I will give you, for example, 5 times 2 plus 3i. So what is this? This number here is a real number. And this one, of course, is a complex number. So when you multiply a real number times a complex number, you will, of course, FOIL. So you will just multiply using the distributive property. So you say 5 times 2 and 5 times 3i. So in multiplication, I multiply real with real, real with imaginary, imaginary with imaginary, and that is not a big deal. So I'm going to say 5 times 2 is 10. 5 times 3i would be 15i. So the multiplication of 5 times 2 plus 3i would be 10 plus 15i. Let us see another case. Suppose that instead of the product of a real number times a complex number, I have the product of the imaginary part times a complex number with real and imaginary part. So 3i times that same value, for example 2 plus 3i. So what are you going to do here? As you see, well, this is an imaginary number or an imaginary part. And this is a complex number with real and imaginary part. So I'm going to multiply here 3i times 2 and 3i times 3i. Right? So when you do that, you get 3i times 2, this is 3 times 2, 6i. And then positive times positive is positive. 3i times 3i, 3 times 3, 9. And I times I is I squared. Now, we know that I is the square root of -1. So if we square both sides, we're going to have, that I squared is equal to -1. So whenever I get an I squared, I say that this is -1. So I have that this is 6i, sorry, let me do it in black. This is 6i plus 9 times -1. So this is 6i minus 9, because 9 times -1 is -9, right? But this is not in a standard form, because in a standard form, I always write the real part first and the imaginary part after the real part. So I have to reorganize my number, and I say this is -9 plus 6i. And this is my solution ready. So in this case, right, my solution is the complex numbers -9 plus 6i. Now, let us now see the multiplication of two complex numbers. So imagine that I have 3 minus 2i times 4 plus 5i. How do you multiply these U-foil? You multiply first times first, outer times outer, the inner times the inner, last times last, right? Right? So if I multiply that way, I have 3 times 4, which is going to be 12. 3 times 5i, that is going to be 15i. Negative 2i times 4, that is going to be negative 8i. And negative 2i times 5i, that is going to be negative 10i squared. Right? So we know that I squared is -1. So this becomes now here 12 plus 15i minus 8i. And then -10 times -1 will be +10. And now we combine real part with real part. So 12 with 10, 22. And 15i with minus 8i, will be 15 minus 8, it will be 7. So we got 22 plus 7i. Super easy. Now, if we have a number a plus bi, we have that the complex conjugate is a minus bi. So why is it important to introduce this definition of complex conjugate? We're going to see why in the next examples. But first, let me give you some examples. So if I have a number that is negative 5 plus 2i, its complex conjugate is negative 5 minus 2i. So basically what I'm doing is just reversing the sign of the imaginary part. If I have one number that is 2 minus 11i, its complex conjugate is 2 plus 11i. So we obtain the complex conjugate by reversing the sign of the imaginary part. So why is it important to know, what the complex conjugate of a number is, of a complex number is? Because if we multiply a complex number times its complex conjugate, the result of that would be a real number. So when I multiply 2 plus 3i with 2 minus 3i, if I use the distributive property here, that means I FOIL this, I will get now 2 times 2, 4, 2 times negative 3i, negative 6i, 3i times 2, positive 6i, 3i times negative 3i, negative 9i squared. Of course, minus 6i plus 6i, that would be 0. So I have 4 minus 9i squared. We know that I squared is negative 1. So this would be 4 minus 9 times negative 1. So this is 4 plus 9. So this would be 13. So the result of the multiplication of, in this case, two complex numbers, very special complex numbers because it was a complex number times its complex conjugate, gave me as output a real number. And it's going to be always like this. Whenever you multiply two complex numbers where one number is the complex conjugate of the other one, the result of that must be a real number. So why is it important to know this? Because when we are doing the division of complex numbers, in some cases we have to use this complex conjugate. So I have to divide complex numbers, So let me start with a very simple example. I have 5 over I. In what consists the division of 5 over I? This quotient 5 over I. Well, basically here what you have in your denominator is a square root, because you remember that I is the square root of negative 1. So if you go back in time, you will remember, that we said that we don't want to have a radical in the denominator of a fraction, okay, because then the expression is not in lowest terms. So when I have 5 over I, this expression is not in lowest terms. So I need to do something to eliminate the I from the radical, and that is just to rationalize. So I'm going to use exactly the same tool that I used to remove radical from the denominator of fractions, so I will rationalize. How do you rationalize in this case when the denominator is just an imaginary part? It's not a complex number with real an imaginary part, it's just an imaginary part. We multiply the numerator and the denominator by I over I. So I will say here that this is 5 times I, 5i, and below I have I times I, what is I squared. I know that I squared is -1, so I have 5i over -1, so I have -5i. So the quotient of 5 over I is equal to -5i. Now, what happens if I have, for example, uh, -7 over 2i? It's a pretty similar case. My denominator is just an imaginary part. I don't have any inconvenience just with this factor 2 in the denominator of the fraction. So my big deal here is about the I. So I'm going to do exactly the same thing that I did in the other case. I don't multiply the numerator and denominator by 2i over 2i. I will multiply by I over I, because as I said, I don't have any problem with the factor 2 here. So if I do that, I will get -7i, because I have -7 times I. In the denominator, 2i times I, 2i squared. 2i squared is -1, so I have -7i over 2 times -1. So it's -7i over -2, so this is positive 7 over 2i. So this is what I get, when I just rationalize -7 over 2i. In these two examples, I had a quotient of, a real number with the imaginary part of a complex number, just an imaginary part. Sorry. So what happens when my denominator is a complex number with real and imaginary part? So let's see the other example. So suppose I have 3 over 2 minus 5i. Maybe you think, okay, I will multiply by I over I exactly as I was doing before. Is you just multiply by I over I here. That is not going to work. And you can just try by yourself. So you are not going to eliminate the I from the denominator just doing that. So when your denominator is a complex number with real and imaginary part, of course, you must multiply by the complex conjugate of that denominator. So basically what I have to do in this case is to say 3 over 2 minus 5i, times, and then I'm going to multiply the numerator and the denominator by the complex conjugate of the denominator. So I'm going to say 2 plus 5i over 2 plus 5i. When you multiply, guys, by 2 plus 5i over 2 plus 5i, you are multiplying really by 1. So you are not changing this. You are multiplying, by 1 in the form of 2 plus 5i over 2 plus 5i. So now you multiply your numerators. So you say 3 times 2 is 6. 3 times 5i is 15i. And then we're going to multiply the denominators. That is 2 times 2 is 4. 2 times 5i, 10i. -5i times 2, -10i. -5i times 5i, -25i squared. 10i minus 10i is 0. So I get 6 plus 15i over 4. -25 times I squared. We know that I squared is -1. So -25 times -1 is positive 25. So now we have 6 plus 15i over 29. And the number like this is not in a standard form, so we must separate real part and imaginary part. So we better split this into fractions. So we say 6 over 29 plus 15i over 29. I cannot simplify 6 and 29. I cannot simplify 15 and 29. So I will leave it like that. So in this case, the result of this multiplication was 6 over 29 plus 15i over 29. I cannot simplify that anymore. So this is the result. This is the complex number we obtain after rationalizing 3 over 2 minus 5i. Let me give you one more example, just complicating this a little bit, because now my numerator will be also a complex number. So I will also show you a shortcut to do the multiplication of the denominators. So suppose that in this other example, this example is example D. So in this example D, suppose I have 3 plus 2i over 5 minus 3i. So I have this quotient here. So I need to rationalize, right? And to rationalize this here, of course, I must multiply by the complex conjugate of the denominator. Complex conjugate of the denominator. So if I multiply by the complex conjugate of the denominator, it means that I will multiply by 5 plus 3i. I multiply numerator and denominator by 5 plus 3i. So common example, some students multiply by 5 plus 3i the denominator, but they multiply the numerator by the complex conjugate of the numerator. That's wrong. To multiply by the same thing, the numerator and denominator of the given complex numbers, right? Of the given expressing quotient of complex numbers. So you always multiply by the complex conjugate of the denominator. If you are rationalizing, you know this denominator. So we're going to multiply just the numerator by FOIL, as we have been doing in all the examples. So I say 3 times 5, 15. No, 3 times 3i, 9i. 2i times 5, this would be 10i. Okay? And 2i times 3i will be 6i squared. And now I will use a shortcut to work with my denominator. Because as you have seen, you know, we always simplify the term with I. So there is an easier way to do it. That is to square the real part plus the square of the imaginary part. So you can always, you know, doing this way, and it's going to work. So it's the same as you say 5 times 5, 25. So 5 times 3i, 59. But negative 3i times 5, negative 59, 59, and minus 59 will become 0. And then negative 3i times 3i is negative 9a squared, so that becomes positive 9. So we have 25 plus 9, and 25 plus 9 will be 34. So that is exactly what I'm going to get now here. We know that this 6i squared, since this is negative 1, this I squared is negative 1, I have now 15, 6 times negative 1 is negative 6, so 15 minus 6 is 9. 9i plus 10i is 19i. And then I have 5 squared, that is 25, plus 3 squared, you know, there is 9. So this is 9 plus 19i, okay, over 25 plus 9 is 34. I will split this 9 over 34 plus 19i over 34. 9 have factors 3 times 3. 34 is not divisible by 3 because the total of the digits of 34 is 7. 7 is not divisible by 3, so 34 is not divisible by 3. So I cannot simplify this anymore. 19 is a prime number, and 34 is not prime, it's 2 times 17, right? But doesn't share any common factor with the numerator, so I have just to leave it like that. I cannot simplify that anymore, right? So in this case, I have used, you know, this shortcut, right? That let me multiply the denominators in this form, you know. So when I multiply a complex number times its complex conjugate, I will always do something like this. You want to FOIL, you can FOIL, right? But you will always eliminate the I terms. The next that I want to explain about complex numbers, of course, is the powers of I. What about the powers of I? Let me show you something. We know that I to the power of 1 would be I, because any number or variable to the power of 1 is the same number of variable. So we know that I squared by definition, is equal to -1. So we know that if we have I to the third, using the property of exponents, you can break it down into I squared times I to the 1. So this is the same that I squared, -1 times I to the 1 is I. So this is the same that -I. I to the fourth power would be I squared times I squared. So it would be -1 times -1, so it would be +1. You find I to the fifth power, this would be I times I to the fourth power. So is I times I to the fourth power. We found that is 1, so it's I times 1, so it's I. If I want to find I to the sixth power, I get I to the second times I to the fourth. I to the second, we found there is -1. I to the fourth power, we know that is 1. So -1 times 1 is -1. Okay, let me go to more. I to the seventh power, we know there is I to the third times I to the fourth power. What is I to the third? We found that I to the third is -I, and we found that I to the fourth power is 1, so -I times 1 is -I. And if I do I to the eighth power, is I to the fourth, breaking this down into I times I to the fourth. I to the fourth, we know there is 1, this is 1 times 1, so it will be 1. And now I want to show you something. I to the 1 correspond exactly with I to the fifth power. I to the second correspond with I to the sixth power. I to the third correspond with I to the seventh power. So have the same values, the same values present, I to the fourth power correspond with I to the eighth power here. And if you keep going and you find now I to the 9, you will find that I to the 9 is I to the 10 is -1, I to the 11 would be -5, I to the 12 would be 1. I to the 13 would be again I to the 14 would be -1, I to the 15 would be -5, I to the 16 would be I. So what we see is a pattern, that is repeating every 4 powers. So that's why when I want to evaluate, powers of 5 where the exponent is a very high number, what I have to do is to divide that exponent by 4, because it's a pattern that is repeating every 4 powers. So for example, suppose that I ask you to evaluate I to the power of 123. Of course, you're not going to go from I to the 1 to I to the power of 123 just one by one. So what are you going to do? You're going to get the denominator, the exponent 123, and you will divide it by 4. Why by 4? Because it's every 4 powers. We get the same value. And 123 is the given exponent. So you say how many times 4 goes into 12 goes 3 times, 4 times 3 is 12, subtracting, we get 0 here. Okay, And then now we bring down the 3. And then how many times 4 goes into 3? It doesn't go into 3, right? So the remainder here, this remainder here becomes the new exponent. So we can say that this I to the power of 123 is the same, that I to the third. And I to the third, we learn, there is -5. So I know that I to the power of 123 is equal to -5. There is another case, I to the power of 252. So if I want to evaluate I to the power of 252, say, okay, let me divide 252 by 4. How many times 4 goes into 25? Just 6 times, right? Because 4 times 6 is 24. Okay. So since 4 times 6 is 24, subtracting here, I get 1. I bring down the 2. So how many times 4 goes into 12? 3 times. 4 times 3 is 12. My remainder is 0. So this would be the same thing that to say this is I to the power of 0, and I to the power of 0 would be 1, right? Because any variable or number to the power of 0 is going to be 1. So I to the 0 would be 1. And like that, you can do it, for an exponent. So 0 becomes here the new exponent. Now, what happens if I have a negative exponent? For example, let's say that I have this case, C is I to the power of negative 73, right? What do? You say, okay, using the negative exponent rule, I know that this is 1 over I to the power of 73. I will remember that I am using this rule, x to the negative n is equal 1 over x to the n. So I will divide 73 by 4. How many times 4 goes into 7? 1 time, 4 times 1 is 4. Subtracting -3, bring down 3 here. How many times 4 goes into 33? 8 times. 4 times 8, 32. Subtracting, I go 1 here. So this will be my new exponent. So that means that 1 over I to the power of 73 is the same as 1 over I to the 1. So this is 1 over I. I'm not going to leave my answer like that because I have I in the denominator, so I will rationalize. So I'm going to say times I over I. So this is 1 times I is I times I squared. So this is I over -1, and I over -1, it will be what? -5. So what is the result in this case? The result of, evaluating I to the power of -73 is -5. So this is how we evaluate, the powers of 5. I have to explain one more thing to finish with this part, with this section, And this new thing that I want to explain is when we are solving equations in the set of the complex numbers, solving quadratic equations. So when we're solving quadratic equations in the set of complex numbers, it's exactly the same thing, So suppose that I have x plus 3 squared plus 25 equals 0. This is a quadratic equation that I can solve easily by taking the square root. So I'm going to say x plus 3 squared equals negative 25, because I just like 25 from both sides. So I have the square root of a binomial equal a number. In this case, the number is negative. It's still a real number, you know. But what happens now here is that when I apply a square root, I get x plus 3 equals plus minus the square root of negative 25. And I know that the square root of negative 25 is I times the square root of 25. So it's going to be 5i. Remember one example that I gave at the beginning. So x plus 3 equals plus minus 5i. Remember, the square root of negative 25 is the square root of negative 1 times 25. So it's equal to the square root of negative 1 times the square root of 25. The square root of negative 1 is I, the square root of 25 is 5. If I have a plus minus in front, I have to keep that plus and minus, right? So I have x plus 3 equals plus or minus 5i. I will be subtracting 3 from both sides. We have then x equals negative 3 plus minus 5i. I cannot combine these two parts, because this is real part and this one is imaginary part, and we don't know subtract different parts. So my solution for the equation is negative 3 minus 5i comma negative 3 plus 5i. So this is my solution for this equation, So my solution for the equation are just two complex numbers. I can solve one more by using quadratic formula, for example. So let me show you one case using the quadratic formula. So let me say 7x squared plus 2x plus 1 equals 0. So if I will solve by quadratic formula here, I know that this is A, this here is B, this is C, right? Remember, ax squared plus bx plus c equals 0. This is the quadratic equation, standard quadratic form. So my quadratic formula, x equals negative b plus minus the square root of b squared minus 4ac over 2a. So negative, what is b, is 2, plus or minus the square root of b squared is 2 squared minus 4 times a, there is 7, times c, there is 1, all over 2 times a, there is 7. So I have that x is equals negative 2 plus or minus the square root of 2 squared is 4 minus 4 times 7, 28 over 14. So this is negative 2 plus minus the square root of 4 minus 28 is negative 24 over 14. So we keep working on this expression, a little bit more. So we have that x is equals negative 2 plus minus I square root of 24 over 14. So it's negative 2 plus minus I. What is 24? 4 times 6, right? So 24 contains a perfect square factor 4 over 14. So this is negative 2 plus minus the square root of 4 is 2, so it's 2i square root of 6 over 14. I'm going to separate now this into fractions, so I'm going to say x equals negative 2 over 14 plus or minus 2i square root of 6 over 14. 2 and 14 dividing both by 2 is 1 over 7, so this is here negative 1 over 7 divided 2 divided by 2 is 1, it's 14 divided by 2 is 7, plus or minus, again, 2 divided by 2, it's going to be 1, so it's going to be I square root of 6, and 14 divided by 2 is 7, so I get negative 1 over 7 plus or minus I squared over 6 over 7, right? So you must simplify. You have a radical expression that can be reduced to lowest terms. You must do it, right? And if when you are here, you have the chance to simplify, you must also do it. And always remember to express your answer, as two independent parts. Real part first, imaginary part after the real part, right? So basically, the solution of quadratic equations in the set of complex numbers is exactly the same, that we work in the set of the real numbers, except that we're going to get complex solutions. So I want to explain something very quick. There is the discriminant. And if in our quadratic formula we have negative b plus minus the square root of b squared minus 4ac over 2a, this expression over here is called d. So d is the discriminant. And d is equals to b squared minus 4ac. Why is the discriminant important? Because when the discriminant is greater than 0, so when it's positive, we know that we're going to have two different real solutions in our equation. When the discriminant is positive, is greater than 0, if you solve the equation, you're going to get two different real solutions. When the discriminant is equal to 0, you're going to have one real solution. There is a double solution. So it's the same solution twice. When the discriminant is lower than 0, you're going to have two different complex solutions. So if you want to know without solving the equation, the number and type of solutions you get if you solve the equation, what you have to do is to find the discriminant, right? And according to the value of the discriminant, greater than 0, equal to 0, or lower than 0, you're going to know how many solutions and what type of solution you are expecting to have. This will be very important, when we when we work with the quadratic functions. So it's something that we're going to see again later in our lecture. So I hope that this lecture helped you to understand the complex numbers. So thank you for your attention, and I hope to see you in the next lecture.